Okay, so we are now interested in testing about our variance and whether this variance is the same as the known variance. Okay, so we are dealing with the one population and one single distribution, and so we have one sample, and then the null hypothesis is this, and the other alternative hypothesis is this guy is different from this known variance. And then we always assume that this H naught or the null hypothesis is true, right? So assuming the true variance is this sigma 0 squared, and then we can obtain this sample variance, and then this statistic will follow this chi-square distribution with the degree of freedom of n minus 1. Okay, and so given this alpha value of maybe 5%, and then in the case of two-sided test, we have this probability and the other probability, right? And then depending on these two probabilities on the chi-square distribution with the degree of freedom of n minus 1, we can obtain or compute the threshold values on the upper side and the lower side. Okay, and then also we studied about how to compute the p-value. Okay, so it can be our statistic or this test statistic computed in this manner can be found on the right side or the left side. Right, so depending on this guy is on the right side, which means the this probability values to the right is less than 0.5, and then we just multiply that value by 2, and that way we obtain this p-value. Okay, and then we extend this situation so that we have now two different distributions. And thus, in this case, the null hypothesis is the two variances are equal or not. Okay, so in this case, so we have these two different sample statistic, which is this sample variance from one population and then the other sample variance from the second population. And then the particular distribution that we try to utilize in this case is something called this F distribution. So F distribution. So what was the F distribution? F distribution was F. I think the F stands for the fraction. Okay, so the fraction, which means we deal with the ratio between some of these two measures, and these two measures are some chi-square distribution of maybe degree of freedom of m and n. Okay, so in this case, we call this this guy as a random variable following the F distribution. Okay, and then this guy has the two parameter of this m and n. Okay, and so we know we know the full shape or the full function shape of this F distribution. So because this measure, like this one and this one, is following the chi-square distribution, right? And so this guy will have the chi-square distribution with the degree of freedom of n minus 1 and m minus 1, right? And then also note that we have two different true variance value coming from the two distribution of x and y, right? And so if we just compute the ratio between the two, okay, ratio between the two, like this, and then we have these two parameters that are seemingly different, but I mentioned that we always start with this null hypothesis being true, right? And so in this case, we can safely cancel them out. Okay, so the ratio between these two, which are these two chi-square distribution, and then they are cancelled out, and then yeah. Okay, so yeah, I was wrong about the F distribution, right? So what was wrong? So we have to have the denominator corresponding to the degree of freedom on each side, each part, right? So this was the F distribution. Otherwise, yeah. So this one will not have the average or the mean value as 1, right? So we are, yeah, kind of comparing like roughly the same statistic or same value. So when averaging them, or when computing the mean of this sum of squared standard normal random variable, and then it will approximately have the mean or average value as 1 and 1, and thus altogether, yeah, this guy will have some mean value as 1. Okay, and so we are canceling out, and then yeah, we can divide it, divide each side by its own degree of freedom. So we are removing these two, and thus just a simple ratio between these two sample variances will follow the F distribution. Okay, and then its degree of freedom will be, yeah, this n comma 1 n minus 1 comma m minus 1. Okay, so in this case, yeah, so let me just change it to follow this notation. Okay, so in this case, it will follow the F distribution with the 2 degrees of freedom. I mean, it has the 2 integer values as the 2 parameter, and they are n, m, m. Okay, then, okay, so we have the table that we can look at in the back of your book, and thus it's a matter of finding a proper value corresponding to this threshold value, and then corresponding to these 2 degrees of freedom. And thus, in the case of two-sided test, yeah, we are obtaining these 2 lower and upper bounds in our acceptance region. Okay, if it is an outside of this region, and then yeah, we conclude that these 2 are having a different variance values. Okay, so I also almost forgot about the F distribution. So let's let's review what the F distribution was. Okay, and so yeah, depending on these 2 degrees of freedom, the probability density function will look like this. Okay, and then among all these cases, which one do you think has the smallest variance in this case? Smallest variance. Yeah, probably like when degree of freedom, the first and the second degree of freedom was 1, 1 and 2, 1, they have a kind of different shape, where they have, yeah, this kind of shape of a monotonically decreasing function. But usually it has the peak around here and here, and then yeah, when degrees of freedoms are really large, okay, of 100, and then yeah, it will have really sharp peak, right? Which means in this case the variance will be really small, right? And then as you saw in this case, so since we are averaging out, or taking the mean value of our chi-squared random variable with the degrees of freedom, and then if these 2 degrees of freedom are really large, and then those 2 values will almost approximately be 1, right? Yeah, so that way they will have really small variance on each of these numerator and the denominator. and thus yeah, they will have overall, this F distribution will have this sharp shape like this. Oh, yeah, this gray colored one. Okay. Okay, and then yeah, in the case of a, for example, like a blue one, of having degree of freedom as 5 and 2, and then it has this skewed distribution, right? So in this case, you can clearly see that the mode is less than 1, right? The value that has the maximum probability density value, that will be less than 1, but overall, the mean value, okay, so the mean value will be around 1, because in that case, the mean value should have the same area when splitting them into 2 parts, right, by using this threshold value. So that's the property of this mean value, right? So it is a it is skewed distribution, and thus when having the mode on the low less than 1, the mean value will be close to 1. Okay, well, anyways, yeah, this F distribution has this kind of shape. And then let's look at this mean and mode. Yeah, so the mean is mean has this. Yeah, I didn't even know, but yeah, the mean is not exactly equal to 1, right? And also interestingly, its mean value is only dependent on the second degree of freedom. Yeah, it's quite, it looks quite new to me. Did we study this or not? We didn't study this? We just skipped it? 네? 아, 내가 옛날에 1이라고 했어요? 네, 그러면 잘못됐나 봐요. 네. So yeah, it will be approximately 1, but it will not be exactly 1. Yeah, sorry about that if I said that way. But anyways, yeah, if degrees of freedom on of this D2 goes to infinity, and then it will become close to 1, right? Yeah. Okay. Okay, so we looked at the shape of the distribution roughly, but yeah, mainly what we need when utilizing this F distribution is just basically a table of this the value of the probability when particular threshold is given, and that probability will be on the right side of the probability, right? So that is the meaning of this value. Okay, and then similarly, I mean, similar to the previous case where we considered this p-value, instead of using a predefined alpha value, okay, so yeah, so we first compute this guy, which follows the F statistic, right? And then this value will be our V, and then we look at the table in the back of your book, and then find the probability corresponding to this V, okay? And then, yep. And then if it is less than 1/2, and then 2 times of that value will be our p-value. But what if it is more than 1/2, and then we just so what if what if this value is having the probability of more than 1/2? In that case, what should we do? Yeah, so we do the same thing of this guy, 1 minus this value, right? And then, yeah, this F distribution has an interesting property as follows. So let's say the two degrees of freedom are 3 and 5. And suppose maybe 7, for example. And then suppose that probability will be something like maybe 2%. 2%. Okay. And then okay. Let's consider this this thing, f3 comma 5 comma 3. Okay, so in this case, it's another f distribution with its own degrees of freedom, completely different degrees of freedom, but they are in a reverse order, right? The reverse order. So when having these two values as 2 degrees of freedom, and then the corresponding threshold value of 7, and then yeah, intuitively, you can think of this value will correspond to what in these in this second f distribution. So it's like x3, yeah, xn equals 3 squared, and n m, yeah, this n is 3 comma 5. So in this case, it was the value of 7, and then if it was 5 and 3, then what would be the corresponding value? It would be 1 over 7, or 1/7, right? Right? And then you can derive some interesting kind of a property about this f distribution. So yeah, so it's my first time actually to derive this relationship. So yeah, so I'm kind of excited and nervous, but yeah. So this one is corresponding to the sum or the integral of starting from 7 to infinity of this f distribution when degree of freedom is 3 comma 5, right? And maybe x, for example, and this one was 2%, right? And then what is the corresponding probability when this x value is infinity? In the case of like f of 5 comma 3. So in this case, yeah, infinity will correspond to, I mean, it's reciprocal, right? So 1 over infinity. Does it make sense? Right? So yeah, just like a 7 corresponding to 1 over 7, infinity will correspond to 1 over infinity, which is 0. Does it make sense? Right? So it will be like 0, and 7 will be like 1 over 7. Does it make sense? Right? And so this one will be what? This one will be also 2%, right? Because all the values from starting from 7 to positive infinity will map to like 0 to 1 over 7, and there are corresponding probabilities, and summing all of them up from this distribution that has this inverse or the reciprocal kind of relationship, the probability will be the same, right? Okay, so yeah, so in this case, so it can be represented by one minus like this value. Yeah, something like f of 5 comma 3 and 1 over 7, which means this guy is a typical kind of threshold value that we care about or that we consider as the probability starting from 1 over 7 to infinity when this f of 5 comma 3, right? Okay, so yeah, So using this guy, okay, f of yeah, so how do I represent that? Okay, so we need this probability and f like 2% and 3,5. So this one will correspond to 7, right? So do you guys remember like the z of 0.025 is what? 1.96, right? So the corresponding threshold value is this value, right? When having this probability. So when having 2% or 0.002, 0.02, okay, and then 3,7 will have the 7, okay, and then what about this? So it is like yeah, so so it was 2%, right? It was a 2%, and then starting from, yeah, so sorry about being a mess here, but what about the probability starting from 1/7 to infinity when summing them up for this f distribution over 5,3? What is the probability? So it is 2%, and that corresponds to this region of from 0 to 1/7. And the probability of, ranging from 1/7 to infinity will be 1 minus 2%, right? So it's 98% of the probability, right? Okay. So f of alpha and n comma m is like this one is 2%, and this one is 3,5, and then this one was 7, right? And then f and 1 minus alpha, which is 98%, and when we reverse NMN as M and N, okay? So in this case, what is that? It is 1/7, right? And so, yeah, this guy is like 1 minus f of alpha n and m, right? Okay, yeah, so it was my first time, but I hope it is correct. Is it? Is it? Has anyone checked the book? I mean, the book should have this kind of relationship. Yeah. Okay, so yeah, F distribution, yeah, because it has this interesting kind of a form. Yeah, in its this form of the fraction or the ratio between these two chi-square distribution. Okay, so we can derive this kind of interesting relationship. Okay, and yeah, related to that, yeah, so it's really an important trick when you study this math and yeah, or at least some math related stuffs. So yeah, probably it will be probably sometime in the middle school when these unknown variables are introduced, like x comma y and z or whatever, right? And so in these cases, yeah, we have to deal with these unknown variables, right? So yeah, that is acting as a main kind of a barrier to understand this intuitively, right? So in these cases, you have to make your own example by just replacing these variables with the specific value, and then they will make it a lot easier to understand and yeah, keep track of what's going on in these derivation or understanding these equations. Yep, and these tricks are really, really important, not just in this class, but also in understanding many other courses, yeah, including like yeah, machine learning and other stuffs. Yeah. Okay. Anyways, that was about the test on this variance being equal or not between the two populations. And in this case, we used the F distribution by forming the ratio between these two sample variance, which follows this F distribution. And then probably the last topic about this hypothesis testing is on this Bernoulli parameters. And in this case of this Bernoulli parameter, it has only one parameter of the probability of seeing the random variable value as 1. So in the Bernoulli random variable, this x value will have either 0 or 1. And then the associated probability will be p and 1 minus p. So this p is the only parameter when thinking about this Bernoulli random variable. Okay, so let's consider these two hypotheses, where the null hypothesis is that our Bernoulli random variable parameter p is less than pre-given or the known value of p0, and also alternative hypothesis is that p is greater than this known value. So yeah, so it can be used in many practical situations where suppose you invented a new medicine, and previously the existing medicine worked only on maybe 10 out of 100 people, which means it will be effective with the probability of 10%. Okay, and then you suppose you invented a new medicine, and then you want to prove that, you want to show that your medicine works much better than the other, which means the probability of your medicine being effective will be significantly higher than 0.1 or 10% of the probability. Okay, so that's the situation that we are interested in. Yeah, in the case of this Bernoulli parameter testing. Okay, and then we typically start with the sample, right, which is composed of an IID observations, right? And then this IID observations, and when collecting all these Bernoulli observations, and that will form our binomial random variable, right, as a whole, right? Yep. So when having n observations in our sample, and then this E of an x will be np, and variance will be this guy. Okay, we know that, right? And then if n is really large, and then we know this binomial random variable, even though it is a, by the way, this binomial random variable, is it discrete or continuous random variable? Is it discrete or continuous? Binomial random variable. It is a discrete random variable. It can only have the integer value as possible value, ranging from 0 to n. Okay, but this can be approximated into a normal distribution when n gets large, right? Even though this normal distribution is defined only on this continuous random variable, right? But as n gets large, the interval between each integer will be really small, yeah, compared to the entire range from 0 to n, right? So that way we can kind of approximately think of it as a continuous random variable. Okay, then yeah, this will be the standard deviation, and then this one has this mean and the variance, and thus x minus np divided by this guy will be approximately the Gaussian standard normal random variable. So the rest of the story will be really easy, right? So we just apply the standard normal random variable on this test statistic, right? But yeah, think of let's see. Okay, in this case, yeah, we are doing one-sided testing here, right? One-sided test, right? So the null hypothesis is p being less than or equal to a particular value, right? And so for this test statistic, our acceptance region should be, our acceptance region be like this guy being less than some value, or should it be larger than some value? I mean, for the acceptance region that will still accept this null hypothesis. Yep. How can we do that? So which one is the correct one? Which one is the correct one? And yeah, when computing this, one kind of tricky issue that we have is in order to compute this test statistic, we have to know the parameter that we want to estimate, p, right? So if you guys remember what we did in the interval estimate when dealing with this Bernoulli parameter, and what was it? So what was this p0? What was this p0? So it comes from this null hypothesis, right? So this is not the same as the trick that we used in the previous chapter, but we use this p0 in the place of this, okay? And then if this p0 was the true parameter, and then x will be having like around 0 values, which is the mean of this standard normal random variable, right? So in the case of this null hypothesis, which is the p value being the parameter value of p, not the p value, okay? The parameter p is less than a p0, and then it means this guy should be less than some value, right? So in that case, we can still accept that this hypothesis is true. But if this was true, okay, in some cases, and then this actually observed random variable x value from binomial random variable will be much larger than this expected average value, and thus the rejection region will be defined as having this particular inequality sign. And then, of course, the threshold value will be this C of an alpha. Okay, and then we see alpha instead of alpha over 2 because we are doing a one-sided testing. Okay. And then in some previous example, we can compute these measures that we need in order to compute this test statistic. And then when x was observed as 10, and then we can just compute this value, and then Why do we see this value of 9.5? Why is it 9.5 instead of 10? I see. Oh, okay. Yeah, that is a very good answer. Yeah, I actually missed it. Yeah, when looking at, when preparing for this slide. Yeah. Okay, so this one is the threshold coming from the normal distribution, which assumes continuous values, right? And then this value is the possible value actually in the discrete space, or our binomial cases. So okay, and then instead of using this, and we use this, and then we compute this statistic to compute this p-value and use it as a threshold value. Okay. And then also we can do the two-sided testings here, right? So in this case, this is the null hypothesis, and this is an alternative hypothesis. Okay, and then this value is our binomial value, which is corresponding to this x value, and then we just standardize it, or we just represent like this equation, so that we have like something like this equation by just moving this to the right hand side and adding them to the right hand side, and that way we can obtain this threshold value on our binomial random variable value itself. And that value is denoted as x in this case. And then if it is having the probability of having this being less than this or greater than this, and then this is when we reject the null hypothesis, right? Because this one or this one is clearly the rejection region. And then also we can compute the p-value as well. And then p-value is defined in this case. Okay, so in this case, on this x value, is the scenario will be the same. So we just compute between the two. We compute the smaller one, which will be less than 0.5, right? So the story is exactly the same as the previous ones, and then okay, so that way we compute this p-value. But in this case, there is one kind of minor difference from the previous case. Why did this guy not write like in this form, 1 minus bin of n of p0? Okay. So it is related to the issue about this distribution being discrete, right? Because it is discrete, so we have to, if we consider 1 minus this probability, and then it will be the same as binomial distribution n comma p0 being strictly greater than x, right? But when we compute this rejection region, we typically include this threshold value, right? And so these two values are not exactly summing up to 1, or it's not like this relationship. So both of them will have this equality sign, and thus their sum of these two probability will be higher than 1 or greater than 1, right? But at least that's how we compute this p-value, because our rejection region will typically include these threshold value. Okay, but still we compute these two and choose the smaller one. Okay, and then 2 times of this smaller value will be our p-value. Okay, any questions so far? And and this is the end of this chapter of chapter 8. And as you may have seen, we skipped some of the last part in this chapter. So we just we skipped these explicitly optional sub-chapters, but also some additional chapters or parts in this chapter, in this big chapter. Okay. So so in that case, it means that you don't need to like study those other material that was not covered in this class. Okay. Any questions about before ending this chapter of hypothesis testing? Okay, then let's move to the next chapter of regression. Regression is really an important topic in statistics, and also like in machine learning, and probably in many other engineering and technical fields or science fields. And there are many different approaches that can derive the solution or the optimal solution for this regression problem. But in this subject or this class, since we are studying this statistic and probability, and we studied the approach to obtaining the solution of this regression problem based on some statistical kind of estimator and so on. Okay. Okay, so there are many texts in this case. It's just copied and pasted from the book. And so we have, this is the setting. So we have a single or scalar response variable, or it is also called a dependent variable. Okay. And then we also have an input associated with this y value, and that input is also called a independent variable. And then we want to obtain this formula that will make this y be equal to these values. So in this case, it's definitely a paired setting. Okay, paired setting. So we have a 2 sample. So we are given 2 sample. So this is a basic setting of this regression problem, but also this is the paired setting. So given a particular x value, and then it is associated with the particular y value. So they are all aligned. Okay, and then also, in the previous example of paired test, let's look at the slide of this paired test. So we had a x and y as the 2 samples, but y was also the scalar values, and x was the scalars as well, right? But what if this x was some joint random variable, Okay. So in this case, we consider the situation where yeah, a person was having a particular height, and then he or she moved to the US, and then his height was changed to a different value, right? So that was the situation we considered. But what if we consider a particular person's like height and weight? Okay, yeah, this is our x as a joint random variable, and y is the same person's maybe life expectancy. Okay, how long he or she lived. Okay, so in this case, still they are paired setting because yeah, each row came from the same person, so that's how we paired them. But in this case, this x random variable x is actually a joint random variable which can have a multiple values. Okay, so that is a basic setting, and in that case, for each pair, we want to build up this kind of equation where this dependent random variable value, or the y value, or in this case, life expectancy value, is actually equal to some linear combination of these height and weight value, which are our independent random variable, or each of these values contained in our x part. And then also we allow some constant as well. Okay, so in this case, our life expectancy y can be represented as maybe height times maybe height times 2 minus and 5 times weight plus maybe 25. Okay. I don't know how much it makes sense, but yeah, we can think of this kind of relation, and let's assume that yeah, this relationship is always true in all the observations that we had in these paired settings of this two random variable, two samples. Okay, so in this case, yeah, what we want to do in this problem setting is to obtain these values. Okay, these coefficient value that will form this linear combination. So these coefficient values are represented or denoted by this beta 0 through beta r. So in the x part, we have r dimensional joint random variable, and then each one will have its own associated coefficient value and some constant. So that is the typical setting. But in practice, this relationship will not be exactly true, right? So there will be some error, right? So we cannot in practice we cannot make this equation true for all the cases, but we will have to admit that this one will be approximately true, and then in order to make them exactly equal, what will be the corresponding error for each different cases, or each different person's like height and weight and life expectancy. Okay, and then if we really approximate it really well, and then overall error value represented by this e will be really small, right? But if we did a poor job on determining those coefficients, and then this error will be really, really large. Okay. So here, how we determine these coefficients in an optimal manner. Okay. So what is the optimal, or what is the best coefficient for these beta 0 through beta r? Is those parameters that will make this error values to be as small as possible. Okay. So that is what we want to do in this linear regression problem. Okay, and then we can represent this by treating this e, or error, as a random variable. Okay, as a random variable. And then we can think of yeah, this kind of conditional expectation when given a particular set of x values. So given the information that a person's height is maybe 175 centimeter and the weight is maybe 80 kilogram, and then what is the average value that we can expect as the y value, or the average life expectancy value. Okay, so in this case, we can think of some expectation on this y, and then we can think about this e of all these, right? And then since this guy, yeah, so e of these and plus e of e, and then let's assume that this error will have the zero mean. Okay, so sometimes e will be like +5 or e will be -5, which means for the person who lived actually up to 75-year-old, but he actually we estimated or we predicted his or her life expectancy as 80, and then we kind of overestimated his or her life expectancy. So that way we can consider this error value, and then we can think of this average value of these error will be 0. Right? And then in that case, it can be set as 0, and then this conditional expectation can be represented in this case. Okay, and then yeah, this is the linear regression problem setting in the linear regression, and this linear regression can be divided into two different problems, where the first one is really easy one, which we call this a simple regression, and then the other one, which is a little bit more difficult one, is called the multiple regression problem. So in this case, the main difference is that this guy is when our sample of x is not a joint random variable, but it's just a scalar random variable. So this is the situation where we are given x as only a single value. So instead of given a weight and height and weight, we are only given weight, for example. Okay. So that is called this simple regression. And then this multiple regression is when we have a multiple variables or joint random variable in the place of an x part. Okay, so this is the main difference between these two. And then we first consider this simple regression problem where y is now represented by this. So alpha, which was our parameter corresponding to beta 0, and then beta 1 corresponding to the first random variable x, and we just enumerate or denote them as alpha and beta, and then plus some error. Okay, then let's look at the example. So again, we have two samples of x and y, and these are just enumerator, index of this sample. Starting from 1 through 10, so we have like a 10 person's weight and the life expectancy, for example. Okay, so in this case, again, they are paired setting, right? So they are all paired, and then we have to think of this equation of alpha plus beta xi plus some error. Okay, so in this case, when drawing these two values, and then we can represent them in this 2D scatter plot form, right? And in this case, if we determine the alpha and beta really well, and then this error will be minimized, right? And then that line will be something like this line. Okay, so this one is not crossing origin, right? So this is not even the origin. And also in this case, when given x value as 50, and then our model is saying that the y value is approximately like this value, right? But actually, the actual sample that we observed will have the error as like this amount, right? So in this case, epsilon will be positive or negative. Which one is the one? Which one is the correct one? So y is alpha plus beta x plus epsilon. So the actual value is this y value. So this value is x value, and alpha and beta is the y-intercept and the slope. And then this value will be corresponding to this value. So epsilon will be what? Negative value, right? But sometimes it is positive, because in this case, yeah, x value was this guy, and then the corresponding prediction of this y value will be here, and this part will be this, and this actual y value will be much higher. So epsilon value will be large or positive. So in this linear regression or this regression problem, we are actually determining this y-intercept and the slope, which corresponds to this alpha and beta respectively, yeah, in an optimal manner. So what do you mean by optimal? It will be optimal when these errors, yeah, all these errors are minimized. So yeah, in this case, suppose the optimal line will be looking like this. But let's say, yeah, another person estimated or determined the alpha and beta in this manner. Okay. So in this case, let's consider the error with this red line. And then the error will correspond to these values, right? Okay, this one will have almost zero error. But in the case of a blue one, you will really have the error as really a large one, right? So the total sum of these errors will be much large. Yeah, in the case of this blue line. So we can see that the red line is much better than the blue line. Okay, and then yeah, we can easily compare between the two given this linear pattern. But we are actually, yeah, we are aiming at determining the optimal value themselves. Okay, what are the particular value that are optimal that will minimize all these error values? Okay, and then how do we sum these, or how do we add up these error values? So sometimes these error will be negative, right? So in this case, the error will be like -3, and in this case, it will be plus 1, and positive maybe 1.5. Okay, and given these errors, how can we summarize them into a single error measure? So in that case, we use a squared sum of these error values. So in this case, the error will be -3 squared and 1 squared and negative 1.5 squared. So this one will be like how bad this line is. Okay, how bad this line is. And then this one will be maybe 12, for example. But in the case of this blue line, the squared sum of these errors will be much larger. So yeah, we can see that this red line is better quantitatively, right? So not just intuitively or vaguely, but we have a way to compare between them in a quantitative measure based on this squared sum of the error value. And then we want to obtain alpha and beta as an optimal value that will minimize this sum of squared error. So that is what we want to do in this chapter. Okay, so the time's up. So let me continue the next Tuesday. Okay, thank you very much.
회귀 분석이 상관 분석에서 얘네가 상관성이 있는 거를 수학적으로 어떤 모델을 제시하는 거잖아요.
네.
근데 회귀라고
왜 회기라고 하냐고요?
명칭이 약간
아, 네, 이게 회기가 뭐 정확하게는 모르겠지만 이게 그러니까 이게 이 회기 분석에서 이제 그 가장 최적의 그 기울기나 이 y 절편을 찾아가는 과정이요. 여기서도 봤듯이 이제 그것들을 최대한 이제 에러를 줄이는 방향으로 되는 거잖아요. 근데 이게 어떻게 보면 이게 이거를 뭐 그 머신러닝에서의 뭐 그레이디언트 디센트나 뭐 이런 걸로 또 이렇게 풀 수가 있거든요. 그러니까 이거를 한 방에 이제 이 에러를 최소화하는 거를 한 방에 찾을 수 있는 어떤 수식이 있고요, 공식이 있고, 그 다음에 또 머신러닝에서는 또 그걸 그레이디언트 디센트라고 이걸 좀 점진적으로 좀 찾아가거든요. 그런 경우 이제 이 어떤 라인의 그 기울기나 y절편 찾아가는 과정이 결국은 저 에러를 조금씩 줄여가는 과정이거든요. 그러니까 그게 어떻게 보면 이제 우리한테 주어진 y 값들을 그러니까 최대한 잘 그 y 값들에 좀 잘 맞도록 이 라인이 이렇게 움직여가는 거예요. 그러면 뭐 예를 들면 점이 뭐 새로이 들어왔어요. 우리가 총 10명의 데이터를 모았는데 한 사람의 데이터가 또 들어왔어요. 그러면 걔가 어딘가에 찍힐 거고 걔에서 발생된 어떤 새로운 에러 때문에 이 라인이 조금 더 이렇게 조정이 되겠죠. 그런 측면에서 얘가 이렇게 뭔가 좀 우리의 데이터를 쫓아간다 라는 측면에서 이제 뭐 회기라는 게요. 좀 그런 의미라고 나는 거예요. 네. 네.
일리 있네.
그렇게 나는 뭐 생각을 하고 있어요. 나름대로. 네.
그거는 또
네.
저 하나만 질문.
네.
그 제가 얼마 전에 로지스틱 클래시피케이션을 해봤는데 이제 그 녀석을 A, B, C라는 결과를 얻어내기 위해서 세 가지 로지스틱을 다 따로 해봤어요.
ABC 클래스가 3개예요.
네, 클래스가 세 개인데
네.
라벨이 각각 A인 라벨이랑 B가 C가 있는 건데
네.
이거를 그 소프트맥스가
소프트맥스,
결국엔
네.
하나를 만들어주기 위해서 하는 녀석.
네, 그 중에 하나만 고르기 위해서. 네.
근데 제가 궁금한 게 그냥 따로 로지스틱을 3번 거쳐가지고 가장 큰 값이 나오는 값을 쓰는 거랑
네.
소프트맥스를 하기 위해서
네.
이 여러 개의 그
네.
웨이트를 한 번에 구해내는 것 그게
네.
둘 중에 굳이 소프트맥스가 더 의미가 있는 이유가 있어요?
소프트맥스가 의미 있는 이유는
네.
그게 그러니까 시그모이드는 결국은 그러니까 시그모이드 3개를 뺀 그러니까 로지스틱을 3개로 따로따로 클래스별로 만든다 하면
네.
네. 그러니까 기본적으로 얘는 상대적인 비교가 아니라 절대적인 좀 비교거든요. 그러니까 로지스틱 리그레션에서 그 리니어 컨비네이션 나온 값이 만약에 0이다.
네.
그럼 정확하게 50%가 되죠.
네.
그러니까 이 특정 A라는 클래스가 될 확률과 안 될 확률은 50-50예요.
네.
이거 뭐 1이면 뭐 대충 2.54니까 뭐 한 75%? 뭐 70%?
네.
뭐 그 정도. 2.54 플러스 1분의 2.54니까.
네.
그런 식으로 해서 얘가 뭐 예를 들면 한 3쯤 나왔다고 쳐봐요. 3. A라는 클래스가 될 확률이 3쯤 나왔어요. 그리고 얘가 진짜 3이 A예요. A.
네.
그럼 3이면 사실 2에 3승하면 꽤 높거든요. 2.5에 한 3승하면 뭐, 네. 그럼 뭐 한 90% 넘게 연절이 좀 나온단 말이죠. 그러면 로스 입장에서는 그 바이너리 크로스 엔트로피 로스 입장에서는 로스가 거의 발생을 안 해요. 왜냐면 그 정도면 잘한 거니까.
네.
근데 이제 이게 바이너리 클래시피케이션에서 각각 따로따로 했을 때 이게 절대적인 어떤 그 기준을 적용을 한다는 의미가 되고요. 이게 소프트맥스는 이게 이렇게 결정이 돼요. 그러니까 얘가 이제 리니어 컨비네이션에서 값을 한 3쯤 냈어요. 이건 꽤 높은 확률을 주는 거였거든요. 시모이드에서.
네.
근데 B와 C에서의 그 리니어 컨비네이션도 또 값이 나오고 걔네들을 다 익스포넨셜을 건 다음에 이제 그 노멀라이즈를 썸 투 원으로 하잖아요.
네.
얘가 3이 나왔는데 만약에 B가 엉뚱하게 리니어 그 컨비네이션에서 나온 값이 5예요. 그럼 얘는 5는 그러니까 3은 이 5한테 당연히 밀릴 수밖에 없어요.
네.
그러니까 상대적인 확률로 따지면 이 3에 해당하는 확률은 뭐 예를 들면 뭐 한 20-30% 이하로 훅 떨어지는 거예요. 이런 경우는 이제 상대적인 어떤 그 세기를 봤을 때 쟤보다 내가 더 어느 정도 이상 높게 나와야지 되는 건데도 불구하고 네 아까처럼 절대적인 기준으로만 따지면 그거를 좀 안 하게 되는 거죠. 그러니까 절대적인 기준으로도 약간은 그게 그러면 절대적인 기준으로 하면 그럼 아예 안 될 거냐 해도 되기는 해요. 그러니까 그게 무슨 소리냐면 3이 나왔으면 얘는 그래도 잘 한 거예요. 그죠? 얘는 만족. 근데 이제 그 두 번째 클래스인 B에서는 그 리니어 커뮤니케이션 했더니 한 5가 나왔다고 쳐봐요. 그럼 5는 시그모이드를 거치면 이거는 2의 5승 플러스 1분의 2의 5승이 되기 때문에 이건 확률이 거의 한 98% 이렇게 나온단 말이죠. 그러면 98%가 나왔다. 그러면 그 값은 얘는 실제로는 B가 아니고 A니까 여기에서 걸려야 되는 레이블은 0의 레이블이 걸리기 때문에 이 98%는 엄청나게 큰 로스를 발생시켜서 얘를 무조건 0으로 다운을 시키려고 할 거란 말이죠. 혹은 0보다 더 작은 값으로. 그러니까 얘는 얘대로 물론 로스가 발생이 돼서 그러니까 이 상대적인 비교가 아니라 이 절대적인 값을 기준으로 이제 누구는 올리고 누구는 내려주도록 하는 로스가 따로따로 발생이 된다고 보면 되고 이제 소프트맥스 같은 경우는 이게 같이 들어가서의 어떤 상대적인 비율만으로 이게 계산이 되는 거기 때문에 그러니까 예를 들면 이런 경우 그러니까 소프트맥스에선 얘가 뭐 한 마이너스 한 10쯤이 나왔어요. 그럼 2의 마이너스 10승 플러스 1분의 2의 마이너스 10승은 거의 0에 가까워요. 이게 진짜 클래스라 그러면 확률이 거의 0에 가까운 게 나왔으니까 굉장히 심각하게 큰 로스가 발생이 될 거예요. 근데 얘가 마이너스 10이 나왔는데 이 B가 마이너스 100쯤이 나왔어요. 그럼 이 경우는 상대적인 비율은 얘는 또 거꾸로 두 개 간의 그 2의 지수승 걸어갖고 분의 1 하면 얘는 확률이 굉장히 크겠죠. 그렇죠? 그러면 로스는 거꾸로 거의 발생을 안 해요. 이 경우는 그러니까 굉장히 해피한 상황이에요. 상대적인 비교에서. 근데 절대적인 비교에서는 그러니까 절대적인 비교라고 하긴 그렇고 절대적으로 따로따로 로스를 따지는 경우에는 마이너스 10은 굉장히 심각한 로스죠. 다른 애들에 상관없이. 이해가요?
네.
그래서 사실 뭐 참 좀 장단점이 있고요. 그러니까 그러니까 꼭 그러면 무조건 소프트맥스만 써야 되네. 뭐 아니면 뭐 무조건 뭐 시그모이드만 써야 되네. 그러니까 소프트맥스만이 뭐 이렇게 뭐 그냥 일단 능사 혹은 걔가 만능이다. 걔를 무조건 써야지. 이것도 아니에요. 그러니까 이게 약간 어느 세팅에서 좀 달라지냐면 기본적으로 멀티 클래스는 멀티 클래스인데 기본적으로 멀티 레이블이냐 싱글 레이블이냐의 이 두 가지 세팅이 좀 이 머신러닝 문제에서 좀 나뉘어요. 그래서 무슨 소리냐면 이게 뭐가 있을까? 그러니까 한 사람이 이제 그 여러 개의 클래스 중에서 딱 하나만 true인 경우가 아니라 여러 개가 같이 true가 될 수가 있는 경우. 그러니까 첫 번째는 뭐 강아지, 고양이, 사람. 이거는 예를 들면 뭐 어떤 한 놈을 골랐을 때 이게 강아지이면서 사람일 수는 없잖아요. 그러니까 하여튼 그러니까 유일하게 딱 하나만 true인 경우예요. 이게 싱글 레이블이라고 불러요. 그러니까 멀티 클래스는 여전히 멀티 클래스인데 싱글 레이블 프로블럼이라고 불러요. 근데 이제 중요한 건 뭐 우리의 그 카테고리가 하나는 뭐 포유류, 뭐 사람, 뭐 글쎄요, 뭐 개구리 뭐 이렇게 있다고 쳐봐요. 그러면 사람은 포유류도 1이고 또 사람도 1이겠죠. 그죠? 이런 경우는 그러니까 레이블이 이 세 개 중에서의 상대적인 비교가 아니라 하나하나를 독립적으로 기냐 아니냐를 따로따로 따져야 되는 문제로 돼요. 이게 이제 멀티 레이블 문제거든요. 그래서 이런 경우는 시그모이드 쓰는 게 좀 더 맞아요.
하나의 결과를 내야 하는 상황이 아니면
그렇죠.
따로 판단을
그럼 거꾸로 멀티 레이블은 소프트맥스로 아예 못할 거냐? 그러니까 아까 싱글 레이블은 좀 더 소프트맥스가 말이 되는 것 같아 보여요. 그럼 멀티 레이블일 때는 그러면 무조건 시그모이드를 쓰고 소프트맥스는 아예 갖다 버릴 거냐? 그렇지도 않아요. 소프트맥스로 할 수도 있어요. 어떻게 하냐? 거기서는 이제 좀 약간의 어디셔널 컨스트레인트가 필요한데, 그러니까 한 사람이 이제 될 수 있는 어떤 한 데이터가 들어왔을 때 얘가 가질 수 있는 어떤 포지티브 클래스의 개수가 3개다. 만약에 그걸 알면 소프트맥스에서 1등만 뽑는 게 아니라 3등까지 뽑으면 돼요.
여러 개 그걸 뽑아보면
상대적인 등수에서 3등까지 뽑으면 돼요. 근데 다만 그게 그러면 예를 들면 그 숫자조차 그 숫자 모르겠죠. 그거 어떻게 알아요? 몇 개 포지티브 레이블을 가진다는 걸 당연히 모르죠. 그러면 사실 그런 소프트맥스로는 좀 한계가 좀 있긴 해요.
예를 들어 포유류 개구리랑 이 사람이라고 하면 포유류에서 개구리 쓰고 포유류에서 개구리, 포유류에서 사람이 쓰는데 포유류 사람하고 뭐 책상 이렇게 하면 두 개에서 하나씩
그래서 이제 그게 좀 어떻게 하냐면 그냥 그러니까 여러 가지로 하여튼 생각을 해볼 수 있다라는 걸 이야기를 한 거고요. 멀티 클래스인데 이제 싱글 레이블이면 소프트맥스 쓰는 게 일반적이에요. 그 다음에 이제 멀티 레이블인 경우에는 시그모이드를 쓰는 게 또 일반적이에요. 그리고 이제 이게 레이블들 종류가 이제 여러 개가 있을 수가 있거든요. 그러니까 가능한 레이블들 종류 중에서 좀 상호 베타적인, 그러니까 하나가 되면 다른 애들은 안 되는 그런 애들끼리를 묶어요. 그러니까 예를 들면 이런 경우가 있어요. 그러니까 가장 클리어한 예가 한 사람을 예를 들면 우리는 이 사람의 나이대를 클래시파이를 하고 싶고요. 10대, 20대, 30대, 40대. 그리고 이 사람의 성별을 또 클래시파이를 하고 싶어요. 어떤 사진이 들어왔으면. 네. 그러면 이거는 기본적으로는 우리의 레이블의 종류는 10대, 20대, 30대, 40대, 50대, 60대, 뭐 70대는 없다 치고 그 다음에 남녀 총 이 8개의 레이블을 가지는데 이 경우는 지금 보면 레이블이 약간은 이런 어떤 기준에 따라서 이렇게 좀 나뉘는 거잖아요. 남녀 중에서 하나를 가지고 지금 남녀의 2가지 레이블 중에서는 이건 상호 베타적이에요. 그 다음에 10대, 20대, 30대 이것도 역시 상호 베타적이에요. 그러니까 얘네들을 하나를 묶어서 소프트맥스, 여기를 또 하나를 묶어서 소프트맥스, 뭐 이런 식으로.
그거 뭐 어떻게 그러니까 이중 전공하고 다수 전공하고 그러니까 궁금했던데요.
네.
이중 전공은 이제 같이 하잖아요. 복수 전공을 마치고 하잖아요. 복수 전공을 하는 과정에서 석사랑 같이 공부를 할 수 있나요?
석사요? 석사는 뭐 학성 뭐 이런 거요? 아니면 석사로, 그러니까 학부를 졸업하고 석사를 들어갔는데 이중 전공을 학부에서의, 네?
네, 그런 의미가 없나요?
그러니까 석사 과정을 진입을 한다는 것 자체는 뭐 일단 학부를 졸업하고 나서가 일반적인 어떤 패턴이니까. 네. 이중 전공은 뭘 하게요? 뭐 복수 전공, 통계나 그런 거. 네. 뭐 좋을 것 같고요, 나도. 네. 수학적인 기초적인 뭐 이런 것들은 좀 그래도 들어둘 수 있을 때 좀 잘 공부를 해두면 이게 좀 위로 애플리케이션 단으로는 올라갈 수 있는데 내가 모르는 게 생겨서 이게 밑쪽으로 가려고 그러면 이거가 좀 힘들고 진입장벽도 있고 그렇거든요. 좀 펀더멘탈한 게 보통 좀 어렵고 시간이 더 걸리고 하니까. 그래서 뭐 통계나 아니면은 뭐 최적화나 뭐 이런 쪽에서의 수학 관련된 이런 쪽 뭐 산업공학과라든가 아니면 진짜 순수 수학 쪽에서의 뭐 여러 가지 그러니까 리얼 어널리시스, 뭐 컴플렉스 어널리시스, 뭐 하여튼 뭐 이것저것 있어요. 수학 쪽에서. 그런 것들을 이중 전공이나 이런 거 뭐 하는 것도 좋을 것 같기는 해요. 네. 근데 사실 하여튼 또 아까 하나 좀 그거를 좀 염두에 둬야 될 거는 뭐 꼭 그러니까 이중 전공을 했을 때 본인한테 이중 전공을 했다라는 타이틀이 주는 어떤 어디셔널 베네핏은 사실 크게 없어요. 그러니까 이 친구가 이중 전공을 했으니까 얘는 그냥 싱글 전공을 한 애보다 훨씬 더 잘하겠구나. 네. 그런 어떤 어드밴티지는 좀 없어요. 그러니까 예를 들면 고려대학교 졸업생과 예를 들면 뭐 XX대학교 졸업 뭐 조금 약간 특보 학교가 있어서 XX대학교 졸업 이거는 확실히 좀 타이틀이 주는 어떤 어드밴티지가 있잖아요. 근데 이제 이중 전공을 했냐 안 했느냐에 대한 어떤 그 간판으로서의 주는 그건 조금은 좀 없거든요. 그러니까 이제 실제로 좀 실익을 좀 추구를 해야 돼요. 그러니까 이중 전공을 함으로써 수학 과목들을 들었을 때 저 이 과목을 가르치는 저 교수가 정말로 잘 가르치고 어쨌건 뭐 공부를 하는 방식들은 뭐 책으로 공부할 수도 있고 뭐 인강으로도 공부할 수가 있고 뭐 다양하게 있지만 기본적으로 뭐 책 보면 뭐 졸리고 재미없고 뭐 물어볼 때도 딱히 없고 뭐 인강도 뭐 좀 비슷하죠. 근데 하여튼 이렇게 수업을 누구한테든 들으면 모르는 부분들은 뭐 그 사람 붙잡고 좀 어떻게든 좀 해결을 볼 수도 있는 거잖아요. 네, 사실 그런 측면에서 그러니까 저 사람이 좀 뭔가 잘 가르치고 그리고 뭔가 내가 배우고자 했을 때 그래도 좀 그런 궁금증을 저 사람은 좀 해결해 줄 만한 사람이다. 그러니까 이런 좀 그래도 퀄러티 있는 강의 그리고 퀄러티 있는 강의를 하는 교수들 그런 사람들이 가르치는 강의들을 좀 위주로 듣는 게 내 생각엔 가장 실익을 추구하는 데 있어서 제일 좋은 것 같아요. 그리고 그런 사람들이 마땅히 없다. 그러면 차라리 인강이 나. 굳이 뭐 못 가르치는 사람한테 가서 인공 전공 과목을 들을 필요는 또 사실 없죠, 뭐 당연히. 요즘은 그리고 특히 또 배울 수 있는 어떤 그런 루트라는 게 유튜브나 뭐 하여튼 인강들이 워낙 요새는 잘 돼 있으니까 사실 그쪽 옵션도 워낙 또 좋아요, 또. 뭐 내 학생들 같은 경우 저기 내 대학원 학생들이나 이런 친구들 같은 경우에도 머신러닝이나 이런 쪽 전공하면서 조금 이제 부족하다 싶은 느끼는 과목, 뭐 예를 들면 이제 인포메이션 티어리 같은 과목들이 있어요. 정보 이론이라 불리는 뭐 엔트로피니 뭐 이런 거 비슷하고, 네. 그런 거 좀 그런 거 좀 공부가 필요한 거죠. 그래서 그런 것들을 실제로 뭐 좋은 인강 뭐 이렇게 좀 뭐 그냥 구글에 치고 나오거든요. 그래서 그런 거 듣고 그냥 혼자 공부하고 그런 친구들이 있고, 그러는데도 크게 뭐 문제는 없고 한 것 같아요.
좀 걱정하는 게 이제 이중 전공을 굳이 생각하는 이유가 이제 또 저희가 통계를 부족하다고 생각할 수 있는데 나중에 가서 또 통계하고 하니까 시간이 많이 딜레이 되지 않을까.
네, 그렇죠. 그러니까 이게 뭐든지 알면 되게 좀 좋은데, 일단은 내가 아는 거를 기준으로 아니면 내가 전공하는 어떤 그 뭐 머신러닝이나 이런 쪽에서의 특정 분야를 나도 하는 건데, 사실 뭐 일단 내 기준으로만 이야기를 하면 좀 하여튼 바이어스가 된 거긴 한데, 통계라 붙은 어떤 과목들을 이렇게 많이 들어주는 게 사실 머신러닝과 직결이 되지는 조금은 덜 한 것 같아요. 근데 그런 거는 되게 중요해요. 베이시안 스태티스틱스나 포스티리어 나오고 뭐 그러니까 맥시멈 A 포스티리어리 뭐 맥시멈 라이클리후드 에스티메이터. 우리가 하여튼 나도 뭐 이 강의에서 뭔가 에스티메이션 뭐 이런 거 좀 이것저것 좀 이야기를 많이 하는데, 그런 것들이 어떻게 보면 내가 볼 때 좀 이런 뭐 머신러닝 쪽에서 좀 중요한 어떤 의미를 가진 뭐 그런 거고. 근데 뭐 기타 다른 어떤 이런 스태티스틱 여러 가지 분포들이 뭐 이런 분포 있고 저런 뭐 물론 그런 것들을 쓰는 머신러닝도 되게 많은데, 뭐 네. 또 그렇다고 내 입장에서는 그런 거를 좀 되게 뭐 아쉬워. 그러니까 그런 거를 알아야 내가 좀 뭔가 좀 내가 하고 싶은 거를 뭐 이런 걸 몰라서 내가 못 한다라거나 좀 그런 느낌은 조금은 덜 받은 것 같긴 해요. 그래서 하여튼 통계도 좀 중요하고, 아까 얘기했던 그런 최적화라는 것도 좀 그게 좀 어렵거든요. 근데 머신러닝에서는 좀 많이 쓰여요. 그레디언트 디센트도 최적화의 가장 기본적인 알고리즘이고, 네, 그런 게 어드밴스된 알고리즘들이 굉장히 많거든요, 사실. 그리고 뭐 SVM이라는 거 혹시 배웠나요? 서포트 벡터 머신.
들어보긴 왔어요.
네, 또 머신러닝에서 또 단골처럼 나오는 어떤 또 한 시대를 풍미했던 그런 또 클래시피케이션 방법인데, 거기서도 쓰이는 게 이제 그 최적화. 그게 다 최적화예요. 특히 그 방법. 그냥 최적화예요, 그냥. 네, 그래서 뭐 내 경우 이제 최적화를 좀 나도 한번 배우긴 배웠어요. 대학원 때 막 A뿔도 다 맞고 그랬는데 제대로 공부를 안 하니까 이게 남은 게 없더라고요. 그래서 그런 부분들은 좀 이제 내가 지금 뭐 연구나 이렇게 뭐 좀 계속 이쪽에 뭔가 공부를 하게 되거나 하면서 아쉬운 적이 꽤 많았어요. 그래서 지금도 되게 좀 공부하고 싶어요. 뭐 하여튼 네, 어떻게 하다 보니 최적화를 약간 찬양하는 것처럼 들렸는데 뭐 꼭 그렇진 않고, 아, 머신러닝 꿈나무들인 거예요. 네.
그냥 급 관심이 생겨가지고
네.
이번 학기부터 보려고
네.
하는데 어렵네요.
뭐
선생님 혹시 교수님께서는 기계학습 쪽 수업 혹시 하시는 거 없으세요?
너 지금 4학년 그 딥러닝 과목 가르치고요.
4학년이요?
네.
아,
네, 뭐 그건 좀 인강을 보고 와서 플립트 클래스라고 그렇게 가르치고요. 네. 그거랑 뭐 나는 텍스트 마이닝 관련한 과목도 좀 가르쳤고요. 네.
기본적으로 학부생들은 안 가르치시, 아니 저는 안 가르치시.
네? 그
4학년
딥러닝은 4학년 과목. 4학년 말고요?
네.
뭐 나도 여기 고려대 이제 온 지 몇 년 안 돼갖고요. 내가 이제 3년 차거든요. 그래서 뭐 다양한 과목들을 아직은 가르칠 기회가 좀 없었을 뿐인 것 같긴 해요. 네. 근데 이거 통계 과목 어쩌다 보니 좀 난 진짜 통계 나 잘 모르는데 나 미치겠어 진짜. 사실 이거 가르치느라고 아주 죽겠어요 진짜.